Okay, we're going to revisit this. I handed this out a couple of class periods ago, and we didn't really get to spend a lot of time on it, but it starts with the definition of acceleration, where acceleration is the derivative of velocity with respect to time. But we'll come back down, and the velocity is the derivative of the position function with respect to time. So for example, let's just jump down here for a minute. If I give you a particular function, say s sub t, and I tell you it's the position function, we can find the velocity of the position function with respect to time if we take the first derivative of it. If we take the first derivative of that, of velocity, that will allow us to find the acceleration of the function with respect to time. So the relationship between these is if you're given the position function, we could take the first derivative to find velocity, and we could take the second derivative to find the acceleration. Okay, so that's the relationship that we're going to see there. Let's just go back up here to read some notes. So acceleration is the derivative of velocity with respect to time. Can be written in that form. To find velocity, we differentiate the position function. These are all different ways to say the same thing that we just talked about. To find acceleration, you can differentiate the velocity. To find time, set the velocity function equal to 0 and solve for time t. Time's going to be a positive value. Remember, this is application. To find instantaneous velocity, so that's velocity at a particular point in time, we'll substitute the value t that we find into the velocity derivative of the position function. Speed is the absolute value of velocity. So once you find the first derivative, you take the absolute value of it at a particular time. That's going to be your speed. Always a positive value. The speed's always positive, but velocity can be negative because it's speed and direction of motion. Okay. And up to this point, we found the equation for the slope of the tangent line. That's what the derivative is. And also, we found it to be the instantaneous rate of change in y with respect to x, the dy dx. Okay, so that's just different notation, different things. Let's work a few examples, some application problems with this in mind. Now that we also have the power rule to be able to find the derivative, and we're not doing that page-long process to get us to that point. Okay, if I'm given a position function here in this time interval, it says find the body's speed and acceleration at the endpoint. So the first thing we got to do, we have our position function. So our position function is given to us. How do you find velocity? Because we need to know velocity before we can find acceleration. How do you find the velocity? Take the first derivative of your position function. So what's the first derivative of this? What's the derivative of 6t? Just 6. And then what's the derivative of this? It's just going to be minus 2t to the n minus 1, which is just minus 2t. So velocity, which is also, aka, it's the first derivative of the position function, right? Okay. We know that speed is the absolute value of velocity. Let me put this in a different color. So speed is the absolute value of our velocity function, which in this case is what? 6 minus 2t. In just a minute, we'll work with that. We'll work with the exact intervals, okay? We'll have two different intervals. We have time interval between 0. We want to check the endpoint, so let's check it at 0, and then let's also check it at 6. So what's the velocity at 0? All right, let's just come over here and say velocity at the interval. So that would be 6 minus 2 times 0, which is 6. So we'll do the calculations over here. And what about velocity at the other endpoint, which is 6? So that would be 6 minus 2 times 6. Okay, so we have a velocity of 6 and we have a velocity at negative 6. That's at our two endpoints, but the speed is going to be, speed here would be the absolute value of 6, which is just 6 meters per second. Okay, what about here? It's going to be the same thing, right? So our speed is the same. So we have velocity at the endpoint 0 is 6, velocity at the endpoint 6 is negative 6. The speed in this case is going to be um, 6 meters per second. What's the other thing they asked us for? Acceleration, right? So if I have velocity, position function, take the first derivative to get velocity, take the derivative of this to get acceleration. So acceleration, let's just say a sub t, which is also just taking the second derivative of the position function. What is our derivative of this? Just negative 2, yeah, 0 here, and then just negative 2. Negative 2, so that's negative 2 meters per second squared because we're doing the second derivative there. It also asks us to find that at the endpoints as well. So if we evaluate our acceleration at time 0, we would just get, there's no variable to plug in, right? So you just get negative 2 meters per second squared. And then that's our time. And then also for, whoops, our other endpoint, which is 6, we would get negative 2 meters per second squared. Okay, the main thing to keep in mind is if you're given position, you find velocity by taking the first derivative, and you find acceleration by taking the second derivative. And then you can evaluate that at any given point. Let's look at another one. Okay, we have a few examples here you can just write down. They're not very difficult to move through, but in number 2, if I give you the position function, negative 16t squared plus 18t plus 20, what is the velocity function? So we just take the first derivative of that, which is going to be what? 2 times negative 16, negative 32t to the n minus 1. Then we just have plus 18, and that's just going to be, let's just say feet per second this time. Some unit per second if I had given you one. What's the acceleration function? You take the derivative of that, so the acceleration function would just be negative 32 feet per second squared. Okay, easy enough. Now if I give you a different, I tell you velocity. This time I'm in the middle, I'm in the velocity, and I ask you for acceleration. This is already the first derivative, so what would be my acceleration? Take the derivative of your velocity function, so I'm going to get negative 32t plus 18 feet per second squared, because we're acceleration. Alright, you may also have the case in which I give you the position, but I ask you for acceleration. Well, that implies that you go from a position to velocity to acceleration. So first thing we would have to do scratch work wise is we would have to calculate the velocity, which is the first derivative of that. The first derivative is going to be negative 32t plus 16 feet per second. But it asks for acceleration, so we take the derivative again and we get negative 32 feet per second squared.